Hello, everyone. My name is Alex Moerschbacher, and I'll be presenting today with Dr. Ha, and we'll be talking about building prediction models for 30-day readmissions among ICU patients using both structured and unstructured data in electronic health records. In this presentation, we will first talk about ICU readmissions and their importance as indicators of quality of healthcare, as well as the importance of building machine learning models using electronic health record data. The methods section will provide an explanation for the data preparation and pre-processing. There will also be an explanation of BERT-Based sentence encoders and why they were used in the combined and unstructured data sets. The experiment and results section will include an explanation of the study cohort, the classification algorithms used, and performance metrics. The results for each data set will be presented. The limitations of the study will also be discussed with identification of future opportunities for improvement. Looking at ICU readmissions. Hospital readmissions is an episode where a patient who has been discharged from a hospital is readmitted again within a specific time interval. High readmission rates of patients are a signal of issues with healthcare quality, as well as a financial strain on both the patient and the hospital. The cost to Medicare of readmissions in 2004 was over $17 billion of avoidable costs. In response to these high costs, legislation was enacted which holds a percentage of Medicare payments to hospitals with a higher rate of readmissions. During the first year of the legislation, 30% of hospitals received no penalty, 60% received a penalty less than 1%, and 10% received the maximum penalty under the legislation of withholding 3% of total Medicare payments. This resulted in a total of $280 million in penalties to hospitals. Research has found that anywhere from 12% to 75% of these readmissions could have been avoided. This high level of avoidable readmission indicates that hospitals are not effectively utilizing preventative measures such as patient education, discharge assessments, and in-home aftercare options, as well as identifying these patients before they're discharged. This also prevents an opportunity for identifying patients who are more likely to be readmitted within 30 days, so patient educators can target these individuals. Looking at electronic health records, the widespread adoption of electronic health records presents an opportunity to build machine learning models to identify high-risk individuals that are likely to be readmitted to hospitals. Electronic health records provided both structured and unstructured data about a patient. The structured data includes the demographics, lab chart results, and comorbidities, while unstructured data includes clinical notes such as discharge summaries of a patient. Previous studies have shown the potential to use EHRs to predict ICU creation, specifically looking at studies that looked at only structured data to identify if a patient who has been readmitted between 7 to 12 times in the past 4 years will be readmitted again. So in this study, we used the MIMIC-3 data set of 40,104 patients who were in critical care from 2001 to 2012. The digital health records in this data set allowed for the creation of machine learning models using structured and unstructured data. Our study used all 2,261 admissions, which resulted in a readmission within 30 days. To create a balanced data set, we took a random sample of the same amount of admissions, which did not result in a readmission to the ICU within 30 days. Looking at the dataset creation, demographic data was included: gender, male or female, age, marital status, widowed, married, divorced, separated, or single, insurance, Medicare, Medicaid, and private, and race. Lab chart values were also used. The lab chart values we included were values which were commonly found in other studies looking at ICU readmission. Since the study did not include time series data, minimum, maximum, and average values for these lab charts were used during the course of an admission. The discharge notes for a patient included a history of present illness, past medical history, medications on admission, summary of patient discharge during the course of stay in a hospital, and condition of the patient on discharge. Medications and follow-up instructions were also included in the discharge notes. Patient comorbidities were also provided in the data set. This data was pulled using ICD-9 codes, which were then processed using publicly available code that generated a Boolean value for each condition listed below. Looking at data pre-processing, lab values which were not reported or invalid were removed and replaced with a null value. From there, nearest neighbor imputation was used to generate values for these records. BERT-based models were used to generate sense transformers for discharge notes. In total, 7 different BERT-based models were used to generate the embeddings. Text data was also used. It was also cleaned before using bag of words on text data. The number of embeddings generated greatly outnumbered the number of structured features being provided. To mitigate this, PCA was used on the combined dataset models to match the number of unstructured features being provided versus the structured features. Readmission outcomes were a binary variable generated by comparing the ICU date of one admission with the next for a subject to determine if a readmission occurred within 30 days. Looking more closely at certain sentence BERT-based models, using just a BERT-based model was due to the massive reduction in computation time. By using BERT-based, we were able to reduce the time while maintaining the same level of accuracy. Looking more closely at the study cohort, 47,338 admissions pertain to 40,104 subjects in the study. Only 4,522 of these admissions were included to provide an equal split between admissions resulting in readmittance and those not readmitted. Limiting factor was the 2,261 admissions that were readmitted within 30 days. The table on the right is a breakdown of positive and negative instances stratified by age and gender. 3 distinct data sets were included in this study: structured, unstructured, and combined. Structured included demographic information, lab results, and comorbidities. Discharging notes were used to generate embeddings from the test data for the unstructured data set, and the combined data set had both the structured and unstructured data. The table on the right shows all the features that were used in this study. In the study, we evaluated the data set with logistic regression, feed-forward neural networks, XGBoost, random forest, and support vector classification. The performance metrics used included accuracy, recall, precision, F1, and AURC. XGBoost was implemented using the XGBoost package for Python. Looking at previous studies, XGBoost is typically one of the highest performing models, and ensemble methods typically outperform XGBoost models by a small margin. Parameter tuning was used to improve the overall score of XGBoost when performing binary classification. Hinge loss for binary classification was used to produce predictions that were either 0 or 1. Number of trees in this model was increased for each data set until overall performance of the model decreased. Feed-forward neural networks are deep learning models used when the data is not sequential or time dependent. As data in the model only moves towards the output, while recurrent neural networks, the data is cyclical. This deep learning model works well for our scenario, as each admission is separate from other admissions in the data set, and the data for each admission does not include any time series data. We fine-tuned the hyperparameters for each data set. The combined data set used a model with 100 epochs and 3 hidden layers with 150, 150 neurons respectively, and activation function of ReLU and a solver of Atom. The structured data set used a model with the same hyperparameters as the combined data set. The unstructured data set used a max iteration of 10,000, 8 hidden layers with 100 neurons in each layer, and an alpha of 0.003 and early stopping enabled. The increase in iterations, hidden layers in the unstructured data set can be explained by the difference in the number of features. In the unstructured data set, there were 767 features, while in the combined data set, there were only 100 features, and in the structured data set, there were only 50. For any parameters not specified here, we use scikit-learn's default parameter for the models. Moving on, so for the results of the models using structured data only, the high scoring model was the random forest model with an accuracy of 61.1%, a recall of 81.3%, a precision of 73.4%, an F1 score of 77.2%, and an AURC score of 73.9%. The random forest model shown here had the second highest AURC score out of all 3 data sets. Looking at the unstructured data, the highest performing model was the logistic regression model using bag of words on the text. The accuracy was 68.5%, the recall was 68.2%, the precision was 71.2%, and the F1 score was 69.7%, and the AURC was 75.7%. The logistic regression model here was the best overall performing model for all data sets combined, structured, unstructured, and the combined. Looking at the combined data set, the highest performing model was the random forest model using STSB distilled base embeddings for the unstructured data, which was further processed with PCA embeddings. The accuracy of this model was 70.8%, the recall was 79.2%, The precision was 69.6%. The F1 score was 74.1%, and the AURC score was 70.4%. As you can see here, the ROC curve graph for the top 5 performing models across all data sets. In this study, we found that deep learning models consistently underperformed non-deep learning models in each data set. A possible explanation for this was it was a relatively small data set with a small number of features. Since models like random forest could have the same parameters applied across data sets, it was easier to find the best tuned hyperparameters for that model and other non-deep learning models. While deep learning models had different hyperparameters specific to each data set, requiring a longer amount of time spent on each model. There are several limitations of this study. Imputation was used for lab values as all lab tests were not recorded for each admission. The time constraint with hyperparameter tuning also impacted results, as deep learning models required a longer amount of time to generate the models in comparison to non-deep learning models. Future opportunities would include the automation of hyperparameter tuning so that model creation is independent of the amount of time available to the researcher, and the inclusion of time series data for lab values. The inclusion of time series data for lab values will replace the aggregate value and give a better image of the patient's health throughout their stay. That concludes our presentation. Thank you.